6D.1, we're going to start by looking at inflection points and the shape of our function. So we've got a quartic function, coefficient of 1 here for the quartic term. So we know that it's going to have some sort of W shape, or the curve is going to be heading up at both ends of our graph, but we want to be able to prove that using our calculus. So the first way we do that is to find and classify all of our stationary points, or letting the first derivative be equal to 0. So our first derivative would be equal to 4x cubed plus 12x squared, take 16. Now to equate that to 0, we could take out a common factor of 4, and through factorization, or alternatively by using our calculator and the polynomial solver, degree 3. So coefficients 1, 3, 0 and negative 4. We get two solutions, one of them being repeated at 1 when x equals negative 2. So x equals 1 or x equals negative 2. So to be able to confirm the classifying of our stationary points, we want to be able to draw in our sign diagram. So it's the sign diagram of f dashed of x, and we include those key values of negative 2 plus 1. So to be able to complete that, we then need to obviously substitute values of x back in to the first derivative. So I'm going to start with 0. If we put 0 in, we would get negative 16. So our result is negative. If you're unsure of the other two, you could substitute large numbers such as 10 and negative 10, or you could work on your calculator using your technology with the graph, seeing that the graph to the left of this point is a negative slope, and after our minimum we've got a positive slope. So that is what we're trying to confirm. If you didn't have your technology, you would need to go through and substitute values, but here we've got technology, so confirming that it's a negative, negative, positive. Before we can go ahead and classify, because we're asked to find the points, we do need to find the location of those. So using our trace option, when x equals negative 1, sorry, it was negative 2, we're at y equals 19. And from the sign diagram, a negative slope into a negative slope, we have a stationary point of inflection. The second one of x equals 1, y must be equal to negative 8. And this time our slope going from a negative to a positive must be a local minimum. So that is part A. The second part of the question, part B, is to find and classify all points of inflection. So for points of inflection, we need to work with the second derivative. So we derive f dashed that we have above it, and that would be 12x squared plus 12. Again, we can take out a common factor. Up here I've also missed the squared, otherwise our solution wouldn't make sense to the one below it, so this should have a x. It is going to change our result. With a squared it would become 24x. So 12 out the front, x can also come out the front now. We will be left with x plus 2. So I was able to identify my previous mistake because our point of inflection on the first sign diagram is a negative and a negative. We know that there's a stationary point of inflection at that location. If I didn't factorize correctly, then I wouldn't have found that second solution. So when we equate that to 0, x equals 0, or x equals negative 2. So sign diagram again required, f double dashed, we're going to have 0 and negative 2. if we look at the shape of the curve, when we are looking at a convex section, which it initially is, our second derivative is going to be positive. When we are looking at the curve when it is a concaved section, our second derivative is going to be negative. And then lastly, convex again leaves us with positive for that sign diagram. So the key thing to look for is the numbers that are the same on the first and the second derivative of -2 are going to be stationary points of inflection. If 0 doesn't exist on the first derivative, then that is not a stationary point of inflection. So we have from part A at -219 stationary point of inflection, and at 0,3 using the original function we have a non-stationary point of inflection. Part C, find the intervals where the function is increasing or decreasing. We're just simply looking at the sign diagram of the first derivative. So we can use interval notation. Wherever that was negative, it is going to be decreasing for x less than or equal to -2. For x is less than or equal to 1 but greater than or equal to -2. And then it is increasing from the sign diagram when x is greater than or equal to 1. Part D, find the intervals where the shape is concave and convex. So that is where we talk about the second derivative and its sign. So concavity occurs when we are looking at the curve becoming more negative, and that's confirmed in between our points of inflection. So it is concaved between -2 and 0, and then it is convex when x is less than or equal to -2 or greater than or equal to 0. Once we've got all that information, we can then sketch the graph clearly showing the features found. We do want to try and be as accurate as possible here with our scale. So we know our stationary point of inflection was at 19 and our non-stationary point, or our minimum, was at -8. So on our vertical axis we want to be able to go from 20, 16, 12, 8, 4, 0, and then -4, -8. And then across here, the scale doesn't need to be the same, but we can go 1, 2, 3, -1, -2, -3. So at 19, -2, we have a stationary point of inflection. At 0,3, we have a point of inflection that is non-stationary. And at 1, -8, we had our minimum. So connecting those dots, it is only a sketch. You can label those key points so it is very clear that that is what they are. But there we have our graph of f of x.